Okay, so we're working on problem number 9, and in this scenario, we want to find the acceleration of the marble when it's rolling down the incline. And since we're solving for acceleration, I can use my torque equation that force times radius is equal to inertia times alpha. And instead of alpha, I'm using A over R. It is friction here that is causing the rotation. So I've got a frictional force. I've got mass times gravity force, and I've got a normal force. And I can use friction as my my rotation, but the problem is I don't know what friction is. I know that it's mu times force normal, and I can definitely find the normal force, but I won't be able to find mu. So since we're not given that value, let's try to solve this problem using the variables that we actually have. We have, let me just draw the force body diagram from a rotated angle. And I'm going to break this into components, knowing that this is theta. I've got mg cos theta, and here I've got mg sine theta. So what I know is that friction is equal to mu mg cos theta, because that's the normal force since these are equal. The only problem is I don't want my equation to contain mu because that's not a variable that's given to me. So what I'm going to do is I'm going to change the axis of rotation so that my axis of rotation is now down here, and my frictional force no longer creates a torque because it's going to be friction times a radius of 0, and the component that does create a torque is the the x component of my mg, just this little part that pulls it down in this direction. So I'm going to create an equation for my new inertia, which is my inertia equation from the center of mass plus my mass times distance, and that distance between these two is going to be r squared. So now I have 2/5 mr squared plus mr squared is equal to 7/5 mr squared. And that's going to be the inertia I plug in here. My force that's creating torque, now that I've moved the axis of rotation, is going to be my component of gravity, mg sine theta, times the distance, which is r, times 7/5 mr squared, times a over r. And then from there, you can solve for a. The r's cancel out, the m's cancel out, and a is equal to 5/7 sine theta. For part B, we're trying to find the speed of the marble at the lowest point of the incline. We've got A here. We can say that the initial velocity starts at rest. We're trying to solve for V final, and we need a distance. So the distance in which it's falling is actually this distance right here. And in order to get that value, we know that this is theta. We've got a height here, and if we're trying to find this distance, we can use opposite over hypotenuse, so sine theta. We know sine theta is equal to h over d, and if I'm solving for d, then d is equal to h over sine theta. So that's going to be my delta x, if I just rotate the axis and call that slanted ramp my x direction. And then from there, you can use your simple kinematics equation. The one that works is your V final squared equals V initial squared plus 2a delta x. And then my initial velocity cancels out. My V final, I can even just square root 2 times 5/7 g sine theta times h over sine theta. And you can see that that reduces down, and I'll let you simplify that on your own. Okay, so for this last question, it's asking the minimum height so that the marble can reach the top of the loop without falling down. This is going to be a conservation of energy equation. We start off with some gravitational energy, and at the top of the loop, we end up with some kinetic energy, both translational and rotational, because it is rolling. And then we also have a height, so there's gravitational energy as well. So what we need to figure out is the height in which we need to launch it. So this is going to be mgh is equal to 1/2 mv squared plus 1/2 I omega squared, which I'm going to make that v squared over r squared, plus mg, and then the height of the loop is 2r. Okay, so from there, we are going to try to identify the height. So we're going to simplify all of this down. I'm going to keep the inertia at the center of mass here, which is 2/5 mr squared. So I'm going to plug that in. Let me make that a fraction. And there's going to be a lot of stuff that we can cancel out. And once you've done this a ton of times, you can already kind of guess what's going to cancel. The m's for sure. And then a lot of the radius, r squared and r squared here, those are going to cancel out. I think that's all I can cancel right now. So let me write everything out. GH is equal to v squared over 2. Oh, that cancels out, so I get v squared over 5, and then 2gr. And then I can combine these together, and I end up with 7/10 v squared plus 2gr, and then I can divide the g from both sides. So h is equal to 7/10. Let me write it as v squared over 10g plus 2r. And what we need to figure out to get the true height is the velocity that will get it over the ramp. And this is the minimum velocity to get object over ramp. And we've done a lot of problems like this already. In order to get the object over the ramp, the minimum value, obviously there's mg pulling down, but we've also got a normal force. But that normal force, if I want the minimum, would reduce down to 0. So there's essentially no, it's right at the point where the surface exerts 0 force on the object. And it's still going in circular motion, so mg is equal to mv squared over r. And we are going to solve for v and plug that in. The m's cancel out here. V is equal to the square root of gr. And actually, I need to square anyway, so it's just gr. So 7 times gr over 10g plus 2r reduces this. And I've got 7/10 r plus 2r. And that would give me 27 over 10 r. So that would be the height that we need to launch it at to get it over the ramp.